So now in this video we have an op amp here, and depending on whether we give a high or low input, we will get a steady voltage rise, which we have now. It's leveled off by now, or a steady voltage decline. It's going down now, and you can see the LED getting dim over time until it turns off, and it's going to level off at some point. And then we can get a steady voltage rise again, where the LED turns on and gets brighter over time until it levels off. So now I have the oscilloscope here attached to the output, and we aren't working with much current here. If we measure other voltages, it could throw them off. But in any case, this is 12 volts. It's 2 volts per division. 2, 4, 6, 8, 10. And it looks like we have an output at 10 volts actually, not 12, which makes sense. So in any case, I'm going to move the jumper to the positive supply right there, and it's making a steady voltage change until we get to 0 volts. That is a ramp. When we go to the negative supply there with our input, we get a steady voltage rise, as you can see there. Again, a steady voltage change is called a ramp. And if we, had the exact same timing going high to low to high, so of course the time it takes me to move from one to the other, it's going to level off a little bit. But if you steadily go high and low for equal periods of time, you would get a triangle wave. So I'm using an op amp, the LM358. There's 2 of them on the integrated circuit. I'm only using one. We have half of the supply voltage set at our non-inverting input, the plus right there. Remember, the output wants to be more like the non-inverting input than the inverting input. We are just given either a full supply voltage or a full negative supply voltage, which is ground, 0 volts, to our input there. We have a resistor, though, between that and the negative supply, and then a capacitor from the output to the negative supply. So if we go to the negative rail right there, we're going to get a lower voltage at the inverting input than we have at the non-inverting input, because this is half, and we're pushing down to 0 right there, and thus, so that'll be low there. This is a higher voltage. We'll have a high output there, and the capacitor will start charging in that direction. And it just works out where, with the feedback and whatever, that it makes a steady voltage change. When you got a capacitor there, its voltage is changing. And so I don't have a good explanation why, but it makes it so the voltage is steadily changed. So that's with the low input there. This will be a higher voltage, high output there. And at some point, of course, the capacitor is going to charge to the point where things stop moving. Now, we go to the positive supply, and that means now we have a higher voltage at the inverting input than the non-inverting input. So this is lower, that output goes low. So high over here, low over there, the capacitor starts charging in that direction when you think of conventional current right there. And again, it does so steadily. So again, I don't have a great explanation for it. Now, the output, its voltage is going up or down to keep these voltages equal. That's what this always does. This output keeps those voltages equal unless it just jumps right from the positive supply to the negative supply. But whenever the voltage is changing, you can see a change happening. You know that these voltages are equal. So, well, it's doing what it needs to keep those equal. This barely takes, any current to charge or discharge, and this is a high value resistor. And so it's going to take, it won't let a lot of current through. But whatever voltage we set, the output has enough power where it can light an LED. So now here's the physical circuit. We got positive supply to pin 8, negative supply to pin 4. Again, we're using 12 volts, not 5 volts. We can look at that at the power supply right there. And a maximum of 20 milliamps of current to protect things. And we probably do have about 8 milliamps of current because this output cannot get all the way to the positive supply, as we saw before. Probably outputs 10 volts since we're using 12. It'll probably fall a couple volts short, especially when you ask for 8 milliamps of current. So we got about 10 volts there. The red LED is going to drop about 2 volts and builds up about 2 volts across it, leaving about 8 volts across the 1 kilo ohm resistor. So we expect about 8 milliamps of current. That works out pretty well. So using 2 equal value resistors, 10K, to the non-inverting input, the plus, again, you always got to power it whether it shows it on the schematic or not. Sometimes it does, sometimes it doesn't. And there's our capacitor at the output to the inverting input. And it says 474 on it, and the 4 is the number of zeros, 4, 7, 4 zeros after it, but I believe that's in picofarads. So we won't worry about that too much. And there's our resistor where we are getting our changing signal right there. So it's to the negative supply. Again, it's going to the inverted, so that makes the LED brighter. Makes the voltage go up if you do it fast enough. And then now we're to the positive supply. We're getting less voltage because, again, we got that inverted and the LED fades down right there. And it's kind of hard to tell with LEDs, but you can get a steady brightness and brightness increase and decrease if you go at the proper speed. But in any case, hopefully that makes sense. Again, I don't have a great explanation for why this gives you a steady voltage change. So, you know, hopefully you can find a better explanation if that's really bugging you that you don't know. But in any case, that's it. Thanks for watching. Make sure you check out one of the other videos I'm posting on the screen and check out the links down below. They all help out a lot. I'll see you in the next video.